Okay, up to this point, we've just been dealing with like pin-connected bodies in general motion. Okay, now we're going to look at when we have sliding connections. Okay, and when we use sliding connections, it's best to use rotating axes to determine that. So that's what we have over here in our picture. Is again, I've got my body; it's rotating. Okay, it's at some point. I've got position of A, B, and the relative position of B with respect to A. So to look at velocity of this, I'm going to take the time derivative of that position equation that we've dealt with before, which is RB equals RA plus R of B with respect to A. So I take a time derivative of each of those. Now, the difference here is now my X and Y axes are not constant. They're rotating. They change direction. So I can't... I need to take that into account. So when I take my time derivative, okay, I'm taking a time derivative of R of B with respect to A, right? This vector right here, okay, which is essentially xi plus yj, okay? So I take a time derivative of that. So it's the time derivative of x times I plus x times the time derivative of I, and then the same thing with y. Now, because this axis is rotating, okay, what I'm trying to figure out is di dt. Okay, which is so if I look at right here, so I'm looking at di. Okay, so that's the arc length. Okay, where the unit vector has a magnitude of 1 times d theta, and that's what I have here. So I have 1 d theta dt. Okay, and that is pointing in the j direction. Okay, so di dt is basically d theta dt in the j direction, which is essentially omega in the j direction. Okay, which if I put in vector form is actually omega cross I. Okay, so the same logic follows in order to find dj dt, which is going to be omega cross j. Okay, so plugging in these values for di dt and dj dt, I get this. Okay, and I'm rearranging things a little bit. So I'm combining the dx dt and the dy dt. That's what I have here. So I have dx dt in the I direction, dy dt in the j direction. And then I'm plugging in again omega cross I for di dt. That's what I have here. And omega cross j for dj dt, which is what I have here. Now rearranging this over here in the first set of parentheses, that is essentially my relative velocity. Okay, that's the velocity of B with respect to A. Okay, and then essentially what I have here is I have omega cross xi plus yj, right? If I kind of rearrange this, which is omega cross r of b with respect to a, rearranging what's inside this parentheses. Okay, which leads me to my velocity equation for when I have sliding connections. Notice this is the exact same answer I had previously, with the one exception that I have this sliding velocity, and this is the the velocity of B with respect to A. Now with pin connections, those are two fixed points. Those points don't move relative to one another. Okay, with a sliding connection, those can move relative to another, so I need to include that velocity as well, that sliding velocity, that velocity of B with respect to A. Okay, I still have translation, still have rotation. Again, I'm just adding this sliding velocity, that relative velocity of B with respect to A, which does equal something when I have a sliding connection. Pin connections, those stay at a fixed distance away. That velocity is not there. Okay, moving on to acceleration, I'm just going to take the time derivative of the equation I just put up there. Okay, so I have dv dt. Okay, and then I have d omega dt times r plus omega times dr dt, right? So that's just the derivative of the first times the second plus the first times derivative of the second. Okay, plus d, that the time derivative of that sliding velocity. Okay, so first looking at omega cross dr dt. Okay, well, we already found dr of b with respect to a dt previously, and that's what I have put right in here in the parentheses. Again, we got that previously in the previous slide. Looking at dv dt, Okay, and this is the relative, that sliding velocity. It's going to be the same approach as I had with dr dt. Okay, where I take, again, I have to worry about the x and the y components since I and j are not constant, they're rotating. Okay, so this is the exact same thing, it's just I'm substituting v in for r. Okay, so it's the time derivative of v in the x and the y direction. Okay, and then I've got the velocity times omega cross I plus the velocity times omega cross j. Okay. Effectively, notice that this looks very similar to what I had for dr dt. It's just I got, instead of v omega and r, I have a omega and v. Okay, so it's the same approach as I got there. Now, plugging all of this junk into that top equation, I get the following. Okay, so again, this is the acceleration of b, this is the acceleration of a, that's translation. Okay, then I have d omega dt cross r, that's alpha cross r. Okay, then I have this omega cross r, that's my normal acceleration, which I had before. Then I have omega cross v here and an omega cross v here, so I have two omega cross v. That's actually what we call our Coriolis acceleration, which was forgotten for years historically, but needs to be in there when we do the full analysis. And then I have my sliding acceleration, which is effectively the first parentheses over here. Okay, so again, keep in mind this is the exact same equation I had previously, except for these last two terms, the Coriolis acceleration and the sliding acceleration. Okay, and these only occur because, again, B can move relative to A. It's not a fixed distance away like it would be with a pin connection. With a sliding connection, these vectors actually equal something. But the first three terms, translation, tangential acceleration, normal acceleration, those are the same as they were before. Again, we're just adding the Coriolis acceleration and the sliding acceleration when I have sliding connections as I do here.